right, we now have the basis where we can start looking at chemical reactions. One way that we sort of study chemical reactions and keep track of what's going on is through the use of what we're going to call chemical equations. Now, before we get into chemical reactions and chemical equations, I'd like to show you one of my favorites, and I'll just set it up here. So what I'm going to do is I'm going to take a flammable liquid. It's an alcohol called methanol. And we're going to take a little bit of that flammable liquid and we're going to place it into this milk jug. And that flammable liquid methanol, we're going to react with oxygen in the air. So there's air in this milk jug, so there's plenty of air around to cause our reaction. And we're just going to watch what happens. Shake it up. Okay. So I've got my milk jug set up with the methanol and the oxygen from the air in it. Okay. Well, I hope you enjoyed that chemical reaction. And what we saw there in terms of the reaction, we tried to describe that using symbolism and using chemical equations. So we sort of represent the process that we saw using symbols. And we call those symbols, we call it a chemical equation. And I'm going to write an incorrect version of that particular chemical reaction on the board here. So what we would say is we took some methanol, and its formula, condensed formula, is CH3OH, and it was a liquid, and that was reacted with oxygen, O2, from the air, and that was in the gas phase, and what was produced is carbon dioxide and water. Both of those were produced in the gas phase. And those hot gases that were produced, they produced, they expanded, and they pushed out of the bottle, and they shot this way, which propelled the jug forward. And now notice this reaction is not completely correct. We'll go over why. You may already see what's wrong with it, but we'll talk about that in a second if you don't already see it. But what we've written here is what we call a chemical equation. It's a way that we symbolize the process that we saw. And when we're looking at chemical equations, what is listed on the left side of an arrow, we call these the reactants. And the reactants are what react, and the process of the reaction is sort of written out by this arrow. And then over here on this side, on the right-hand side, are the products. This is what is produced as a result of the chemical reaction. You'll notice that we have behind each participant, the symbol of each participant in the chemical reaction, we have either a L or a G in this case. The L stands for liquid. The little g stands for gas. You might also see this. You probably guess that's going to stand for solid. You might also see this, AQ in parentheses. That's short for aqueous. And that means that that particular substance has been dissolved in water. So we will see this later on, so keep those in mind. Okay, now we're going to talk about what is listed on slide 3 of your PowerPoint. This is a big idea in all of science. It's the law of conservation of matter. And in the context of this chemical equation, we're going to think about it this way. It's that the number of atoms that we have in the universe, that's the number we have. That's not going to change. So if we start with a certain number of carbon atoms, you're going to end with a certain number of carbon atoms. Another way of thinking about it is if I start with 10 grams total of my reactants, I should end with 10 grams total of products. Now I'm lying to you a little bit, just a little bit, but we'll worry about those complications if you take higher level chemistry courses. But for this class, we're gonna imagine that if I start with 12 carbon atoms and those atoms react, on the reactant side, I should end with 12 carbon atoms after the reaction's over. So let's look at this particular equation here and see if the law of conservation of matter has been obeyed. If I analyze this, I check all the atoms that I have over here, and sure enough, there's one carbon. And if I analyze all of the atoms in my product, there's only one carbon. So far so good. Let's check out our hydrogens. Well, I have 3 plus 1 is 4 hydrogens, but I've got a problem. On my product side, I've only got 2 hydrogens. So according to the way this particular chemical equation is currently written, it can't be. It's not like there's going to be 4 carbon atoms, and as a result of a process, 2 carbon atoms are magically going to disappear from the universe. That doesn't happen as far as we know. And so there's an issue here. All right, so let's try to balance this thing to make sure we've got both correct numbers of atoms on both sides of the reactants and products. So if I analyze this and I look at it, my carbons are good. You always leave oxygen to the end. Oxygen is usually the ones in these chemical equations that make it difficult. But you'll notice I have 4 hydrogens over here, 1, 2, 3, 4, and 2 over here. So I'm just going to add in another water to balance it. Now my carbons are balanced and my hydrogens are balanced. Well, I'll check my oxygens, and those are usually tricky. But you'll see I have 1, 2, 3 oxygens on this side, and doggone it, I got 4 on this side. So there's a mismatch. The easiest thing I can do to sort of fix this is if I'm going to think about this in terms of moles and not molecules. I can have 3 halves of a mole. I can't have 3 halves of a molecule. But if I write 3 halves of an oxygen, of a mole of oxygen, I can't have 3 halves of a molecule of oxygen. Well, let's see. 1.5 of O2, that's going to be 3 oxygens. So that'd be 1, 2, 3, 4, and 4. So this would be balanced. Now, if you like whole numbers, which I do, I don't like writing equations like this. Well, let's see, I better put 2 of these because there's 2 waters. If you don't like having fractions in your chemical reactions, chemical equations, which I don't, I'm just going to multiply everything by 2. So this gets multiplied by 2, and it becomes 2 methanols. This gets multiplied by 2, so that's 3 oxygens. This gets multiplied by 2, 2 CO2. And this gets multiplied by 2, that's 4 H2O. Just to make sure, we'll step back and make sure everything's balanced. 2 times everything in here. So that's 2 carbon atoms. 2 times everything in here, 2 carbon atoms. Carbon's good. Let's go to hydrogen. 2 times a total of 4, that's 8. 4 times 2, that's also 8. Now we're going to do oxygen. 2 times 1, that's 2. 3 times 2, that's 6. So that's a total of 8. And over here I have 2 times 2, and 4 times 1. 2 times 2 is 4, and another 4, that's 8. We've got a balanced chemical equation. It obeys the conservation of matter. The number of atoms we have on one side is equal to the number of atoms we have on the other side. Everything's going to balance.